Hi, I am Anuj Kumar and I am a second year CSC student at BIT Chennai. Today we shall be discussing the applications of finite automata in search engines. Let's continue. So first let's have an introduction to finite automata. Finite automata are mathematical models used to simulate a system with a limited number of states. They operate by reading inputs one symbol at a time and determining whether a sequence or a string belongs to a specific language or not. Finite automatas are essential in computer science for pattern recognition, which is a core function in search engines. There are two types of finite automata. First one is deterministic finite automata. So these are the finite automatas where each state has a unique transition for each input symbol. Deterministic finite automatas are memory efficient and are commonly used for exact pattern matching. Whereas non-deterministic finite automatas are used where multiple transitions are possible for a single input symbol. NFAs can be converted to DFAs and are flexible for handling complex patterns. Both types are used in search engines to recognize patterns and filter relevant information from large datasets. Now let's have a look at how the finite automatas are relevant to search engines. Like, why do we use them in search engines? So finite automata are fundamental to search engines because they enable efficient pattern matching. Search engines rely on this technology to scan and match user queries with index data, allowing quick retrieval of relevant content. Finite automata, particularly effective in tasks like keyword matching, filtering content, and processing regular expressions. Now, first, we should understand how search engines actually work. We'll take this in two steps. First, we'll briefly have a look at what are the major steps in working of a search engine, and then we'll dive deep into each of them. So, search engines work by first step here is crawling. In crawling, we collect data from websites across the internet. After that, we perform indexing. In indexing, we organize and store the data for quick retrieval. After that, we have query processing. It matches user queries against the index data. And in the very last, ranking and retrieval. That is delivering the most relevant results to the user. Finite automata play a role in the query processing and ranking phases by recognizing specific patterns or keywords in user queries. This is a pictorial representation of how a search engine works, which might help you understand it in a better manner. Now, let's dive deep into it. So, first step is crawling. Search engines use web crawlers, or they are called spiders, to systematically browse the web and discover new or updated pages. These crawlers follow links from one page to another, gathering content as they go. Next phase is indexing. The crawled pages are then processed and stored at an index, a massive database containing information about the words and topics covered in each page. These allows the search engine to quickly retrieve relevant pages during a search query. Ranking algorithms. Search engines apply complex algorithms that consider factors like relevance, keyword frequency, page structure, backlinks, and user engagement to rank pages. Each factor helps the search engine determine the most useful page for a given query. Next up, we have query processing. When a user enters a query, the search engine interprets the keywords, applies spell checks or suggested corrections, and retrieves matching results from the index. Last, we have result display. The search engine sorts and displays the ranked results on the search engine results page, also called as SERP, SERP. Each result typically includes the page title, URL, and a brief snippet of text. Finite automata play a role in optimizing parts of this process, particularly in areas like keyword matching, spell checking, and filtering results. Now, how finite automata actually helps in following all these tasks, we'll have a look at it. So this is again a schematic representation of this workflow. You can have a look at it for your reference. We have already discussed all of these phases in detail. So, role of finite automata in text searching. Finite automata are used in text searching to quickly recognize patterns in large datasets. When a user submits a query, Finite automatas help search engines locate instances of keywords or phrases in text data, significantly reducing the time needed to search through extensive databases. Regular Now we'll discuss the relation between regular expressions and finite automata and what regular expressions exactly are. So, regular expressions are patterns used to match string within text, commonly used in search queries. They are often translated into finite automata for efficient processing. Search engines use finite automata to parse and match these expressions, allowing for complex searches such as wildcards and partial matches. Next, we have keyword matching in search engines. We'll look at how the finite automata is actually doing its magic in keyword matching. Magic in keyword matching. What a great phrase. One of the core uses of finite automata in search engines is keyword matching. When a user enters a search query, the search engine breaks down the query into keywords and uses finite automata to match these keywords against stored documents. This process helps identify relevant documents that contains the user's query terms. A similar representation is also given here. These are several states, and these are the inputs that the finite automata expects for each state so that it can transit from one state to another state. That's how finite automata processes strings. Next, we have spell checking and suggestion mechanism. Search engines use finite automata in spell checking and auto suggestion. By recognizing patterns similar to the user's input, finite automata can suggest corrections for misspelled words or incomplete queries. For instance, if a user types technology, the system can suggest technology all by itself by identifying common variations of the input pattern. Next, we'll have a look at web page indexing with finite automata. Finite automata assist in web page indexing by helping search engines pre-process text data. During indexing, finite automata scan documents to tag and organize keywords or phrases, making it easier for search engines to retrieve them later. This indexing process, enhanced by finite automata, ensures fast access to relevant data. Filtering inappropriate content. Finite automata are used to filter out inappropriate or irrelevant terms by matching queries against a predefined list of restricted patterns. This filtering ensures that only suitable and relevant content is displayed on the results page, providing users with a safer browsing experience. Next, we'll see the efficiency and speed of DFA. Like we have already discussed what a DFA is. Now we'll see how it is efficient and how fast it is in performing all of these tasks. And why use DFA? Why not NFA? So DFAs are particularly efficient for search engines because they require a single state transition per input symbol, leading to quick pattern recognition. Unlike NFAs, DFAs do not backtrack, which makes them ideal for high speed, low latency applications such as search engines that require fast query processing uses DFA. Now we'll have a look at the algorithms that are based on finite automata in search engines. First up, we have pattern matching, also known as Knuth-Morris-Prep KMP algorithm. The KMP algorithm is used in search engines to efficiently find occurrences of a word or phrase within a larger body of text. KMP creates a partial match table, allowing the search to skip over unnecessary comparisons by leveraging the structure of the pattern. This leads to linear time complexity, making it highly efficient. KMP is specially useful for locating keywords in search queries within index content. Next, we have Aho-Kuresic algorithm. Aho-Kuresic builds a finite automaton that processes multiple keywords at once, making it highly effective for multi-pattern matching. It uses a trie structure combined with a failure function to ensure that a mismatch occurs. The automaton can fall back to a previous state, allowing it to continue matching over keywords without starting over. This is ideal for filtering inappropriate content or performing searches with multiple keywords, where a high volume of data needs to be scanned quickly. Next, we have regex, regular expressions. We have already discussed what regular expressions are. Regular expressions leverage DFA to perform complex matching within text, allowing for more flexible keyword searches. Search engines use finite automata to convert regular expressions into efficient state machines that can quickly match patterns or search for data. Regex-based machines enable search engines to handle user queries that involve partial words, spelling variations, or advanced search operators like wildcards. At last, we have Levenstein automata. Levenstein automata are used for approximate string matching, where small differences are tolerated. By building a state machine that accepts word within a certain added distance, like spelling errors, search engines can suggest correct spellings for similar terms even when the user makes typing errors. Levenstein automata are critical in spelling corrections and did you mean kind of suggestions. These algorithms optimize search engines' ability to retrieve relevant results by making pattern matching and keyword searching faster and more accurate. Now we'll discuss other methods that are used by search engines, and after that, we'll look at why finite automata is more useful. So, first, we have Boolean search. In Boolean search, it uses logical operators such as AND, OR, and NOT to filter search results. It provides precise results but can be too rigid, leading to missed relevant pages. Next, we have vector space model (VSM). Represents documents and queries as vectors in multi-dimensional space, calculating relevance based on cosine similarity. While effective, it can be computationally intensive. Next, we have machine learning algorithms. Technologies like decision trees and neural networks analyze user data and patterns for ranking results. These models require substantial training and can lack transparency in decision making. Next, inverted indexing, a structure that maps keywords to their locations in documents for quick retrieval. While efficient, it is limited by its reliance on exact matches and can be memory intensive. Now, let's have a look at advantages of finite automata in search engines. Finite automata offers several advantages in search engines. First, speed. Yes, it's fast. DFAs process each input with fixed transition, making them fast for query handling. It's very memory efficient. DFAs can be minimized to reduce memory usage, which is critical in handling large data sets, and it's adaptable. Finite automatas can support complex patterns, making them compatible with a variety of search requirements, from exact matches to wildcard queries. Now we'll have a look at some search engines which are using finite automata currently. First, we have Google, the very famous Google. It employs finite automata for various tasks, including parsing search queries, matching keywords against index content, and managing complex pattern matching for spell checking and suggestions. Next, we have Bing, uses finite automata to optimize its indexing processes and search query handling, enhancing the speed and accuracy of search results for users. Next, we have Yahoo Search. It implements finite automata in its query processing systems to improve keyword matching and ensure relevant results are returned quickly. Last but not the least, we have DuckDuckGo. It incorporates finite automata for handling privacy-focused searches, utilizing them in content filtering and query parsing to provide accurate results without tracking users. There are many more browsers that use finite automata, but we are not discussing all of them here. These are the major browsers that are very popular that uses finite automata in their search engines. And this is again a schematic or a pictorial representation of all of these browsers. Now we'll look at the challenges and limitations that are faced by finite automata. Despite their advantages, finite automata face challenges. First, memory consumption, where we can control the memory that is you can see used by our DFA. Sometimes DFAs can also use significant memory due to the number of states required for complex patterns. That is not in our control. If the pattern is complex, we have to use more number of states due to which the memory consumed by DFA increases. After that, the pattern complexity. NFAs can result in state explosion when handling intricate patterns, making it difficult to scale for very large data sets. These limitations are managed in search engines through optimization techniques. Now we'll have a look at the future prospects of finite automata in search engines. Finite automata will continue to play a crucial role in the evolution of search engines. First up, we'll have a look at the key trends that are following in future. Improved query processing. We can use finite automata to enhance understanding of complex queries for more accurate results. AI integration. AI is booming these days, and combination of AI and machine learning with finite automata for adaptive and personalized search experience can be a great addition to have for all the search engines. It can really make our experience much better. Next, we have multimodal capabilities. Efficient handling of text and image queries can also be a future prospect for finite automata. Now let's jump to the conclusion part. In conclusion, finite automata are essential in enabling search engines to perform efficient and reliable searching, indexing, and filtering for text. They provide a fast, scalable solution to complex text processing needs. Now, as we have discussed, finite automata has been used by several search engines for quite long now to perform all the search operations, and it will be used in future as well. So with this, thank you for your attention. Bye.